All right, here we go. 2.9 logarithm expressions, and Aiden's going to read. Here we go.
Important concept. Every operation has exactly one inverse operation. We learn the inverse operations because these will allow us to solve equations involving various operations.
All right, beautiful. So what's the opposite of addition?
Subtraction.
Subtraction. So that's how we'd solve. And what would be what would be the opposite of multiplication?
Division.
Division. That would be our inverse operation. Well, what's the inverse operation of cubing something? What kind of rooting? Cube rooting. And that leads us to what we're doing now. And so what is the opposite of exponentiation?
Logs.
Logarithmics. Now, what's an inverse, by the way?
Switching of x and y.
Love that. All right, keep going.
Recently, we learned about exponential functions and their properties. We would like to solve equations involving exponential functions, which creates the need of an inverse operation related to the exponential.
Oh, good thing we have this. Good.
Big idea. Just as we can write rational numbers in decimal form and fraction form, we can also write equations in
Exponential.
or
What do you think?
logarithmic.
Look at you guys.
These forms create equivalent statements that represent the same claim. We are not changing the problem, we were converting back and forth. We are simply rewriting the equation in equivalent form.
All right, so again, we're just kind of manipulating the way it looks to solve what we need to solve. All right, now I am a fan of Michael Jackson, and so back in the day with Jackson 5, he had a little song with the Jackson 5, remember? It's easy as ABC. 1, 2, 3, baby, you and me, girl. All right, remember that song? Remember that song? And so this is the way I want you to read it. I want you to read it like this. And so I am going to try out for the voice soon. I'm going to win. I know. Oh, my gosh. All right, so log base A of B is equal to C. Say it with me. Log base A of B is equal to C. And the way we solve it is we have A to the C is equal to B. All right, ready? Here we go. Log base A of B is equal to C. And how do we write that in exponential form? A to the C is equal to B. And if you got that, we got it. All right, that's really what a logarithmic is. All right, and so it's basically just switching the place of x's and y's, and we can solve for it that way. All right, Aiden, keep going.
Notation. If the base of a log expression is 10, this is called a common logarithm and is written without a base. For the example, log 3 is understood to have a base of 10. Log 3 equals log
Base 10
base 10.
of 3. Good. All right, and so if it doesn't have anything, it's implied to be what? A base of 10. All right, that's all we need to know there. All right, so example 1, so we're going to convert from exponential to log. All right, so what's my A in this case? 3 squared equals 9. What's my A? 3. What's my B? 9. What's my C? 2. So then I write it as log base what? 3 of 9 is equal to 2. It's easy as ABC. All right, so here we go again. So now I have 10 to the power of x is equal to y. Well, I'd have log base what? 10 of y is equal to x. Now, do we technically need the log base 10? No, I could just write that as log of what? Y equals x, because I don't need that one because it's explicitly known as 10. All right, cool. This one, I have r to the t equals w, and so I'd have log base what? R of w is equal to t. All right, let's do it again. And so now I have y equals e to the 3x. And so now I'd have log base what? E of y equals 3x. Now this goes into a note here. And so does anybody know what log base e is?
Natural log.
It's a natural log. All right, so log base e is the same thing as a natural log. All right, and we need to know that. And it's ln because it's root, and because it's not nl because n is natural and l is logarithmic, and so it kind of bothers me that it's ln, but it's because of its Latin form. All right, so anyway, that's why it's ln. Does that not bother you guys? on these, we're going to convert from logs to exponentials. So we need to go back and forth on this one. And so again, if I understand my ABCs, it's as easy as 1, 2, 3, baby, you and me, girl. And so what would be my A in this one? 7. And what do I raise it to the power of? 2. Which would be equal to x. All right, let's do the next one. And so now I have x equals log base 3 of y. And so what's my A? 3 to the power of x is equal to y. Very nice. All right, and let's look at this one. So now I have log base what? 10. So now I have 10 to the power of 2, which is equal to y. I forgot. I wanted to keep going on this. That's not how it will be written. It will be written as what? Natural log of y equals 3x. All right, cool. Now we're going. So now I have natural log of c, which is equal to 4. Well, what's the base of this one? E. And so this would be what? E to the power of 4, which is equal to c. Good here? Cool. We're moving. All right, and so now we're going to basically solve them. And so Aiden's going to keep going. Here we go.
Sometimes we can evaluate log expressions without the use of a calculator by utilizing its equivalent exponential form.
Evaluate.
Evaluate the following expression without a calculator.
Fantastic. Now, I know this is an expression, so it doesn't have an equal sign. However, the way that I like to think about it is I'm going to put it equal to something. And so the way I'm going to do this is I'm going to say it's equal to c. Okay? I know this is not technically what it is because it's an expression, it's not an equation, but I'm going to make an equation because we can solve for it easier this way. All right? Because how do we solve a log? Log base a of b equals c, so how do we solve for log? A to the c is equal to b. Awesome, possum. All right, and so now I have what? What's my a? 2 to the power of c, which is equal to 8. And so 2 to the power of what gives me 8? 3. And so c is equal to 3. So the answer to log base 2 of 8 is actually equal to 3. Cool, we're moving. So now I have log base 5 of 25. And so I'm going to set it equal to c. And so now I'd have what? 5 to the power of c is equal to 25. And so what does c equal? 2. And so log base 5 of 25 is equal to 2. All right, cool, let's keep going. And so this one I'd have equal to c. And so now I'd have 2 to the power of c is equal to 32. And so 2 to the power of what gives me 32? Zach? 2 times, how many times? 5. Very good. And so now I'd have c is equal to 5. All right, this next one, I'm going to say it's equal to c. And so now, what am I raising to the power of c? 10. So now I'd have 10 to the power of c, which is equal to 100. And so c is equal to 2. All right, this next one, I have log base what? 16 of 4 is equal to c. And so now I'd end up having 16 to the power of c, which is equal to 4. Well, what happened? It's a fraction. What kind of fraction? 1/2, because it's really a what? A square root. And so c would equal 1/2. All right. All right, this next one, I'm going to set equal to c. And so now I have what? 3 to the power of c, which is equal to 1. Well, what must c be? 0. It'd be 0, because anything raised to the power of 0 is 1, except for never mind. 0. All right, we're not going to go that deep. All right, this next one, I have log base what? 10 of 10 is equal to c. And so now I'd have 10 to the power of c, which is equal to 10. So what does c equal? 1. Awesome. All right, this next one, I'm going to set it equal to c. And so now I'd have 6 to the power of c, which is equal to 1 over 36. Well, what happened here? What do I know about my exponent here? It's a negative. Why is it a negative? It goes to the basement. All right, got in trouble upstairs. And so what negative do I need? Not negative 6, negative 2. All right, and so 6 to the power of negative 2 would be 1 over 6 squared, and so I'd end up having c equals negative 2. All right, 6 to the power of 6 is like 40-some thousand. Anyway, it's really big. All right, let's look at example 4 now. We're going to bust out our calculator on this one. So these first two examples, log base what? 10 of 9. And so we're just going to use our little common log. And so we're going to press that into our handy dandy calculator. And we're going to round to how many? 4. We're going to round to 4. And so we end up with log of 9, which is equal to 0.9542. All right. And so what's my next one going to be? Log of what? 6125. And so I type that into my handy dandy calculator and I end up with love it. All right. Pretty good there. All right, these next two is a little bit more challenging. And so I need to have you go to a different spot on your calculator. So do you see your math button on the left? See your math button? Press your little math button. And then you're going to scroll down until you get to A. And do you see how it says log base? All right, I'm going to take a picture of this for our lesson. And so you're going to see what's called log base. And then you're going to press enter on that thing. All right. And so now once we have log base, do you see how it has the opportunity to change in your little spots? All right. And so then you're going to type in a what? A 2 and a 10. All right. And so we're going to press in 2, log base 2 of 10. We're going to press enter. And handy dandy, it goes to 3.3219. Because again, how many are we going to round to? 4 decimal spots. All right. All right, so this next one we have log base 7 of 135. So again, how do we get to it? We press what? Math and then go all the way down to log base or the A. And so then we're going to type in 7 and 135. We end up getting what? 2.5208. All right, so everybody know how to use their calculators now? All right. Miranda, I heard, is nice, so she's going to read the next part. Here we go.
One useful purpose for logarithm is when dealing with exponential data. Exponential data can be very challenging to display graphically because the values may start out very small, but they grow quickly. It is difficult to create a display that effectively shows the smaller values along with the extreme large values. The population of English America and the current United States since 1620 has grown exponentially. The estimated population is shown from 1620 to 1820, where t equals 0 represents the year 1620. The graph on the left shows the population using a normal scale on the vertical axis, because the population expanded into the millions. The data points representing the years 1620 to 1700 are almost indistinguishable. It would be difficult to notice any differences in population during those beginning years. The graph on the right uses a logarithmic scale base 10 for the vertical axis. Using a logarithmic scale allows us to view all the data points relative to each other.
All right. So do you see how like this graph, you can't really see what these things are? It looks like there's basically 0 people in America at this point in time. Does everybody see how that works? And so if you use a logarithmic scale, so this is going to be called a semi-log plot later on. We'll talk about this more as our lesson goes on. But this is going to be a logarithmic scale, so it's 10 to the power of stuff. And so can you kind of see like more of a population here? All right. And so you can kind of see all of them going on instead of just the later ones. Does everybody see how that happened? All right, and so let's look at this example. All right, so in example 5, the population of English Americans current in the United States in 1840, 1860, and 1880 are given below. We're going to plot these on the graph above. However, we're going to put it in a logarithmic scale. So what we're going to have to do is we're going to take the log of its population. And it's a base 10 because it's 10 to the power of. All right, and so what we're going to do is we're going to just find the log of 17,069,453. We end up getting to 7.2322, and so when we plot this, I'm going to have 10 to the power of 7.2322-ish. All right, and so now we'd have that. All right, and so now we're going to find log of 31,443,321, all right, in the year 1860. 7.4975. And so this is 10 to the power of 4.7 or 7.4975. And so I would plot that kind of there. And so then I'd have my logarithmic of my next one. And what do we get? 7.7006. Love it. All right. And so then I would plot that one. All right. And so now we'd see that kind of logarithmic curve. All right. So let's look at the next part. Miranda's going to keep reading.
One common type of graph with a logarithmic scale, the vertical axis includes grid lines as seen below. This type of coordinate grid is likely to appear on the AP pre-calculus.
All right. So this is going to be a lesson later on. However, I'm going to intro things here. I think it's actually a good intro for it. And so if you look at these lines, these go by ones. All right. Now they are not spaced out evenly. Are you following me? All right. And so these goes by ones. And then what do you think these lines go by? Tens. Then what do you think these lines go by? 100s. All right. And they're written for us mostly for like things like physics and chemistry and things like that. So here we go. So we're going to plot 1, 20. All right. And so here's where 1. Okay. So here's our input. And then I need to get to 20. And so this one's 10. And so we'd end up with 20 right here. All right. And so there is our A. And so B, it's 2, 300. Well, our 2 is here, but then 300. So this is 100. And then this would be what? 200. And then this will be 300. All right. And so now I'd be right there. And so C would be 3, 2. Well, these go by what? Ones. And so this is 1, and then this is 2. And so now I'd end up with 3, 2 right there. All right, and so in part D, it's 4, 15. And so 15, is 15 actually on this graph? No. However, these go by what? Tens. And so this would be 10 down here, and then this would be what? 20. And so it must be in between them. It must be in the middle of those. And so D happens to be right there. And then E, I'd have 5, 350. Well, it's 350 on a line. No. And so it must be between 300 and 400. And so this would be 100. This would be 200. This would be 300. This would be 400. And so 350 is in between those. And so that would be E. All right. All right. How do we solve a log? Log base A of B is equal to C. So how do we solve a log and put in an exponential? A to the C is equal to B. What is natural log actually? Log base E. All right.